Let me just say one word about hypocoercivity. So apparently it is a word which has been coined by somebody who is in the other room, and since there is some partial retransmission, I have to be very careful with the words I use. Okay, so Thierry Gallet, to mention him. Okay, so it's really a pleasure. I will try to retrace a little bit what has been done over the last 10 years with specifically L2 methods, which is, so hypocoercivity is the big word to say that we are trying to build a norm in which you have coercivity. And I will try to present you some recent advances, because we realize that actually the framework that we initially developed for a very specific case can be adapted to many situations, and I will try to give you some kind of classification being rather loose. I will not try to treat all the details or mention the limiting cases. Also, I will be a bit sloppy on some references, especially on the probabilistic side, because, well, first of all, there are specialists in the audience, and second, because it would take the whole hour to retrace the contribution of everybody. So I already apologize for those I'm not going to quote properly. Okay. So here is the plan of the lecture. So I will try not to start too fast and explain a little bit what is the abstract method and the motivation. So how the technology works and how you can implement it in some special cases. There are two assumptions which are basically Poincare inequalities, and I will say it's the compact case when these two assumptions are satisfied, when you have the two Poincare inequalities. There is a notion of spectral decomposition which is hidden behind this method, so I will illustrate it on the case of the Fourier variables and present very quickly some results. Now, the non-compact case, which is probably the more interesting case, or the more recent one at least, is one of these Poincare inequalities is missing, and the message is that you can replace it by another inequality, and then you get the corresponding rate. And if time permits, I will also present some application to the Vlasov-Poisson-Fokker-Planck system, which will be the only weakly nonlinear case I'm going to consider in this lecture. Okay, so let me start with the first part and the abstract method. One of the key motivation for this method was to be consistent with the diffusion limit. So several times in the lecture I will mention it because this is part of the requirements that we have here. So this story started long ago, 10 years ago, with Christian Moore and Clément Moore and Christian Schmeiser. And, well, the abstract framework is the following. So you have an evolution equation on a Hilbert space. You have typically a collision operator, a linear collision operator, which can be either of Fokker-Planck type or scattering type, linear one, and a transport operator, which is here. And the basic property we want to address are the fact that L is emission and T is anti-emission. I'm speaking of emission and anti-emission because I want to use Fourier variables, so I want to be able to work with complex variables. Okay, so now the key tool in our method is to introduce some operator A, which is of this form. So P is the projection onto the null space of the collision operator. T is the transport operator. Star denotes the adjoint. And this operator is 1 plus Tp star Tp, the inverse of it, applied to Tp star. And I will try to explain you why we want to introduce this. So, next slide, if I manage it. Oops. Okay, so there are four assumptions, basically, that we need to use. A microscopic coercivity assumption, which says that there is a Poincare inequality when linked with the local equilibria associated with the collision operator. So it is minus LFF term controls the distance to the orthogonal of the kernel here with some constant with a small m to mention microscopic coercivity. There is a macroscopic coercivity which acts on the position variable, so think to an external potential V, a measure which is e to the minus v dx, and what you require is a Poincare inequality for this measure. So this is typically what you want to have. So this is something which involves the operator t here. Here it is a parabolic macroscopic dynamics condition that you see, for instance, when you take diffusion limit. So it's a compatibility condition when you make an expansion order by order in a Hilbert expansion, for instance. And here, well, it is the garbage. So these are the quantities that you get when you do the computation. And the assumption here is that you want this quantity to be bounded by the distance to the local equilibrium. And of course, when you go to practical cases, this is what you really have to prove, and this is the nasty part. So now the very standard observation is that when you have an equation like on the previous slide, the operator L is typically a degenerate operator, which for instance acts only on velocities. So you cannot expect to have global coercivity in the sense that the LFF term can control the distance to the kernel, but it cannot control how the kernel evolves. So if the kernel is made of all Maxwellian functions, for instance, well, you have rho of x e to the minus v squared over 2, and the problem is that rho of x is not at all at equilibrium, and that's what you want to control. So it's the interaction between the t operator and the L operator that you want to control, and it's clear that the standard norm is not appropriate for that if you want to look for instance, exponential rates of convergence. So you have to modify this norm. So the idea is very simple. You perturb, you introduce a kind of a twist here by using this operator A, which is here, and you perturb the original L2 norm. So let's go directly to the computation. You use the evolution equation, you compute the time derivative, you get an entropy production term with a minus sign here, okay? And you have two good terms, which are the LFF term, which controls the distance to the local equilibrium, and a new term, which is ATPFF, which is the one that you are going to use to get the macroscopic coercivity, that is the control of the convergence of the spatial part, the x-dependent part in the kinetic equation. Okay, and then you have all these bad guys, which essentially I assume are well behaved and can be controlled by the two first ones. That was my fourth assumption. So with the four assumptions that we had, then the entropy production term controls the entropy, or this norm h of f, with some constant lambda. Here there is a parameter delta that you have to take small enough, or not too big at least. And the lambda here depends on delta. I will comment on it if I have some time. And the point is that this term here is just a perturbation of the norm because we built A in such a way that it's a bounded operator. So you have the equivalence of the norm. So here this tells you that h of f along the evolution is exponentially decaying with a rate e to the minus lambda t. And once you have this, you have the exponential decay of the L2 norm, of course, up to some multiplicative constant. Okay, so here is the result that you can state using the four assumptions. You can find an explicit lambda, which depends on the various quantities that I had in the assumptions. Also on delta, you can pick a delta and a lambda here, such that this quantity has a sign. I will come back to this a bit later. And this gives you the rate. Actually, the quantity you need to optimize in terms of lambda and delta is this quantity. You want this to have a sign, to be, how do you want it to be? Non-negative, I guess. So you can, for any delta which is admissible, you can pick the largest lambda, and then it makes lambda depending on delta. I will show you where it comes from. Okay, so this is, the abstract result. Well, the proof of this result is not so complicated. It fits essentially on one slide. So you have the two good guys on the entropy production, the one coming from the collision operator here, the one coming from the additional term, which is here, it is ATPFF. And what they do is that the collision term controls the distance to the local equilibria, and the other one is going to control the macroscopic part, the x-dependent part. So really think to PF as rho of x, where rho is just the spatial density associated to a kinetic equation. Okay. Now, the assumption H4 is just made in order to control the bad term, so this is not a big deal. And the observation, the important observation is that this operator A is built in such a way that, well, you can essentially invert it as a solution of an elliptic equation just by writing that J equal AF just means that TP star applied to F is J plus, well, I had the inverse of this operator applied here, so I put it on the other side. And the TP star TP, just think to it as minus a Laplacian, typically. So it gives you an elliptic equation for J that allows you to compute it in terms of F. And that's, so this, the correction term, the AFF term that we have been adding, is a non-local term built by solving this elliptic equation. Once you have this, you can start building estimates. So for instance, if you multiply this thing here by what? By how is it? If you multiply it by J or F, no, come on. Sorry, you take this equation here and you multiply it by J, so you get a G square here. And using the jointness, you get TPJ, the L2 norm of TPJ, which is here. But on the other hand, since G is AF, you are actually computing TAFF. Now, this quantity, of course, you can also use a standard elementary estimate like a Cauchy-Schwarz inequality, which tells you that this TAFF is actually controlled by the norm of the TAF term and the norm of this, because TA is already in the orthogonal of the kernel. Okay? And for instance, by completing a square, you have the control by the sum of the square of these two terms with coefficients here. So for instance, if you take m equal 1, you get mu equal 1, you get, mu equal what? 2, you get this identity, or if you take mu equal 1/2, you get this one. Okay? So it tells you that AF is a bounded operator and TFF is also a bounded quantity in terms of the distance to the local equilibria. So it is typically the kind of manipulation that you can do using the elliptic equation. Okay, so if you decompose the norm into the component on the kernel of the operator and the orthogonal component, and I call them x and y, actually getting a sign for entropy minus lambda times, entropy production minus lambda times the entropy just amount to look at the condition for this quadratic form in x and y to be non-negative. And you see that for delta small, well, here you have a lambda m, here you have something which is of the order delta, and this is a cross term which is also of the order delta, so it's clearly controlled by this. You could even control the square root of delta. Okay? Now, the term that comes from here is here, so you can discuss and try to, for a given delta, try to optimize lambda or vice versa. So in the end, the result that you get is that the entropy initially is controlled by the norm, the initial norm, up to the coefficient for the equivalence. Then you evolve it by the time and you get the exponential decay. And once you have the entropy at time t, it controls the L2 norm in this way with an additional constant. So this is a typical result of this hypocoercivity result, you get an exponential decay for some parameter delta, which depends on the way you build the norm. And there is a prefactor, which is always bigger than 1 because you have used twice the equivalence of h and the norm. Okay, so if you are interested in getting something which is as close as possible as the initial norm, maybe you want to take this constant as close to 1 as you wish, so take delta going to 0, but then the price you pay is that the decay is not so good. So there is a balance depending on what you are interested in. Good. Now, I told you one of the motivation came from the diffusion limits. So here is the formal diffusion limit made on the abstract evolution equation with the transport operator T, the collision operator here, L here, except that I already put the parabolic scaling in it. So I get an epsilon in front of the df over dt term. I'm looking for large time behavior. And I put a 1 over epsilon, which tells me that I have many collisions, so I force the convergence towards the local equilibrium. So formally, if you Taylor expand in powers of epsilon, you can plug this into the equation, and assuming that you can solve order by order. At order epsilon minus 1, you just have this term, so you are in the collision of the operator, so it means that the this term here is actually in the kernel of the collision operator. For a Fokker-Planck, a linear Fokker-Planck operator, you are a Gaussian in velocities, but not in space. At order 0, you have a first relation, and this is where the assumption H3 enter. This is the compatibility condition, which allows you to express F1 by inverting this. So you have to do something here. Actually just taking this. And then you plug this in the order of epsilon equation, which is here, which is not completely convenient, but if you compose it with the projection, then you get this. And if you remember that U is a kind, F naught is a kind of spatial density that I call U, then the equation you get here is a diffusion equation. So you have achieved the goal, which is to see that the spatial diffusion in the diffusion limit obeys to a diffusion equation which also has some exponential convergence rate. Now, the game with this operator A is to reintroduce this TP star TP in the correct place and use it at the kinetic level. That's all. Okay? But the motivation definitely came from here. Maybe one more, very, very basic toy model that I like very much actually. So imagine that you have a U which is made of two scalar components, U1 and U2. And you apply this evolution equation with a collision operator which is coercive but only in the second component, and an operator T which is a transport operator, so it's antisymmetric here. Okay? And of course, if you compute the time derivative of u1 square plus u2 square, you don't see the antisymmetric part, so you just see the coercive part, which is coercive only in the second component. So you have the decay according to this. So if you take a diffusion limit, but here there is a limit, so that would be getting something like the limit of u1 is proportional to minus k2 u1, and that's the decay that you are expecting in the diffusion limit. Okay, of course, it's not true for this equation here. It's just after taking the limit that you have this. That's why there are some parentheses here. And, well, the idea of the generalized entropy is just to make some twist on the coordinates. So instead of taking the usual norm, to combine u1 and u2, exactly like you do with the hypocoercivity method developed by Cédric in the H1 framework. But here it's at the L2 level. So if you do this, well, it's just a brutal computation. You get a bunch of terms. You get a cross term that you can control by this term, which is essentially the coercivity result that you have here, and this additional term which comes from the cross term and which gives you a good control on the macro part, which is here. Okay? So you combine them and then you get the rate. So the picture is the following. If you just look at U1 square, well, it has some oscillating behavior. Oops, sorry. If you compute it. If you compute the original L2 norm U1 square plus U2 square is the one which is here, which has 0 derivatives each time U1 square is maximal here. And so which means U2 equals 0, by the way. And so the decay here, we have 0 derivatives, so there is no hope to get some exponential decay. But what you look for is actually that the envelope of this is, there is an exponentially decaying envelope. And that's what you capture with this H, which now has non-zero derivatives here. This is the derivative plotted here. And this is the one that was on the previous slide. Okay, so you see the idea is extremely basic. We introduce some twist in the components, or if you make a spectral decomposition, you introduce some twist for each of the modes, and that's the way it works. So, okay, it's a bit a long story. Some of the ideas were already present in the paper of Clément Moore and Lucas Neumann. Frédéric Hérault gave in 2006 some decomposition based on the Witten Laplacian, which has essentially this feature, except that he was not interpreting it in terms of diffusion limits. And in terms of diffusion limits, actually this paper turned out to have been very inspiring, but this is an old story now. And these are the two papers in which we developed this, so already some time ago. So the toy model I showed you shows that there is really something behind the spectral decomposition. So this is something that you can really try to take advantage of. And I will quickly present some Fourier mode-by-mode decomposition based on the Fourier transformation. And yeah, okay, I shouldn't spend too much time. So it's some work which has been done essentially 2 years ago with a group of people who are here. And the two examples that you have to keep in mind are the linear Fokker-Planck operator, where you have a Gaussian local equilibria, or the linear relaxation operator, again with Gaussian equilibria. So this is the linear Btk. These are the two examples on which you can test everything. Of course, you can do much better. So for instance, for Fokker-Planck, you can allow for non-exponential, non-Gaussian equilibria, which are here. And then you have to enter a little bit more in the details. So here I am in the compact case, so I'm assuming that this. I also need some minimal growth at least, so that there are moments of order at least k. I don't want to go too much into the details. So if you take Maxwellian Gaussian equilibria, everything is simple. If you go away from these equilibria, things become a bit more complicated because, for instance, the matrix of the tensor matrix against the local equilibria, so essentially the matrix of the second moments, well, it involves some constant theta, which is maybe not the same as the one that you get from this quantity, of course, except if you are on the Gaussian. Okay? So you have to introduce all these notations, which can be summarized here. Well, the only thing you have to keep in mind is that in this good case, you have a Poincare inequality. So for Gaussian, the Gaussian Poincare inequality, which tells you that this quantity against the Maxwellian controls the L2 norm against the same weight here, of course, up to the kernel, which is made of the constant. Here is just in velocities. Okay, another example is the generalization of Btk. So you can use a linear scattering operators with some sigma here, which needs to have some properties. You can eventually even relax this, but this makes life much more simple. So you assume that they are bounded from above and from below. This is the standard example. In that case, you get this. And otherwise, you need to be a bit more precise. For instance, if you don't assume micro-reversibility, well, you still may have local mass conservation. This is okay. But then with the previous assumption, there is a paper of an old paper of De Gong, Goudon, and Poupeau, which proves that you have a microscopic coercivity property, which tells you that LFF, actually, the local the collision operator has a spectral gap, and that you have this inequality here. Okay, no, next one. Okay, but keep in mind that these two examples are the one on which you can really understand the machinery. Now, if you are in this specific case, you can of course do much more because you have a nice spectral decomposition. Essentially, if you put some confinement in X with some harmonic potential, for instance, on Hermite functions for this operator, and also you can do plenty of things in the linear Btk case. And this idea has been pushed quite far by a group of people, essentially in Vienna, with Anton Arnold, Barleitner, Stürzer, and for the Btk part with Carlen as well and other collaborators. And you can give sharp conditions and build mode by mode what is the optimal norm, and build the norm for which you can get really sharp decay rates. But of course, it's very specific. You really need to have lots of information on the spectrum. So this is not the direction I'm going to, well, in some sense, yes. So now let me take another point of view, which is the decomposition in Fourier mode. Okay, so you just do a Fourier transform, but you do it in the x variable. Why do you do that? Well, it's because the transport operator now becomes a simple multiplication operator, which is very nice. So now the Fourier variable associated to the position, which I denote by xi, is now can be considered as a parameter. And for each value of xi, you can apply the abstract lemma, the abstract result. So that's the strategy, okay? So, well, okay, just a few slides to show you that this is really tractable things. So the space here, xi is considered as a parameter, so I fix it. If you work on the torus, xi is just made of integers. If you are on the whole space without confinement, well, xi is a real valued vector. Okay, and actually you can play with both cases. Okay, so here I apply the abstract result, but just with the v variable, and I freeze the xi, I take it as a parameter. So it is the mode by mode decomposition. Well, the projection is still the projection on the local Maxwellian. Sorry, I'd say Maxwellian, but you can take more general local equilibria. Say Maxwellian to make things simpler. The transport operator is just the multiplication operator, so you can really compute with it and get explicit quantities involving the parameter and local quantities, microscopic quantities. This is the integral of f dv. The macroscopic coercivity condition is just the fact that when you compute TPF, you apply T, well, you take the square of T, so you get essentially a xi square. Against the Maxwellian, you integrate V square, and this is why you get the theta here. H3 is just a symmetry condition, and you have an explicit, an explicit expression for the operator A, which involves the flux. Okay, so it's xi scalar product with the flux, normalized by the 1 plus xi square, which comes from taking the inverse, which in this case is a local thing. Okay, so this is one type of computations. Okay, so very briefly, just to convince you that you can really carry the computation, if you compute AF, you express it, you split it, you make a Cauchy-Schwarz inequality, you get an expression in terms of the distance to the local equilibria, which tells you, by the way, that you have a bounded operator. Okay, if you are dealing with the scattering operator, you have this. This is the Poupeau-Goudon and Degon result. For the Fokker-Planck operator, for instance, you can compute terms like ALF. And again, you see that you have something like this. So remember, we had this ATP term, which we were using to twist the norm. Okay, so if you put an additional t, you are going to get an additional xi, so you're going to get a xi square here, which is probably on the next slide, if I can get it. Yeah. So the ATPFF, sorry, it is a mistake here, it shouldn't be here, is exactly computed as this, okay, which is a nice bounded operator. And you get a control on the PF term. Well, the other terms are control, and then you use a few elementary estimates depending on psi to get some explicit estimate of the parameters of the abstract result in terms of the parameters of the capital theta and small theta. Okay, so this is typically the result you get mode by mode. There is an exponential decay with a rate that is explicitly computed in terms of the quantities which were on the previous slide. Sorry, I'm a bit fast because I have plenty of things to say, and I shouldn't be too long. Okay, so first application, which is completely trivial, is that if you use Parseval formula or Plancherel formula, well, here you're in the torus, so you just sum the discrete modes. Because the first mode is the psi as integer coordinates, you have a gap for free. So you automatically get an exponential decay result with the same lambda as on the previous slide, except that you are losing a little bit because of the psi coordinate. Yeah?
Sorry, could you just recall who's going on?
Sorry?
Could you just recall who's going on? What is going on?
Oh, gamma, sorry. It's here, it's m dv or 1/, it's m dv. Yeah, yeah, sorry. Yeah, thank you. Okay, so it is a result, and yes, and that's a point. It's a Gaussian measure in velocities, which is a rather small space. So then one of the nice aspects of this method is that you can use the factorization method of Gualdani, Mouot, and Michler and Mouot. And, well, you can just actually apply a special case of this by making a nice splitting of L minus T in two operators A and B. Use some regularity properties that you have on these operators. And you can essentially expand. So instead of having Gaussian weights, or when you write F over the Gaussian and put the inverse Gaussian weight, if you replace the inverse Gaussian weight by some polynomial weight, then you get the result which is here. Again, I'm going to skip it very quickly, but gamma k, instead of being, yeah, so I should have been more careful. Okay, so I withdraw what I was saying. The previous gamma was 1 over the Maxwellian in the case of Maxwellian equilibria, and I claim that you can replace it just with weights with polynomial growth using the factorization result. Sorry, my notation are not very good at this point. Okay, so this is standard, and I don't want to insist on this, but you can really get results of decay in rather large spaces for which spectral properties would not be so straightforward to write from the beginning. Okay, the machinery, as I told you, is essentially to compute the entropy production, the minus lambda times the entropy, collect the terms, evaluate the cross term in terms of the x squared and the y squared. This one comes from the ATP FF term. This one comes from the collision operator. Okay, and you have minus lambda, which is collected with the bad terms here. Okay. And the game is to make this quadratic form in x and y now non-negative, and this is the way you can take the best choice for the parameter lambda and delta. Well, there are other things you can play with, so I will not emphasize it too much, but when you take the inverse in the definition of the operator A, well, the goal was actually to get a bounded operator with a spectral gap. But putting identity plus TP star TP is a choice, but there are other choices. And for instance, instead of putting the identity, you can put epsilon times the identity. So in Fourier variable, it will be replacing this by this. And this is very good if you are interested in optimizing on the rate. But of course, there is a price to pay, and the price you pay is that in the decay result, the constant which is bigger than 1 becomes very large. Okay? So it depends on what you want to optimize, but if you are interested in numerical application of this method, it is good to play with delta, lambda, and eventually it is epsilon here. And if you go to fractional diffusion, you have more things to play with, but I will not mention it in this talk. Good. Another example, which was in the initial paper with Clément and Christian, is what happens when you have the good case, or a confinement. So you have an external potential V for which you have a Poincare inequality plus a few additional properties, because when you solve the elliptic problem that you need to use to invert the expression in A, you need a little bit of elliptic regularity, and for this you need some additional property of the potential. So typically, well, you want to have some potential V such that you have a bounded measure, you have a Poincare inequality, and you need a few gross conditions which are here that are needed to get the elliptic estimate. So I'm going to skip it very quickly, but this is the result that gives you this hypocoercivity result in this good compact case. Good. Yes?
What's the parameter eta on the previous slide?
Okay, it's just to insist that the constant here is bigger than 1, so eta is a positive parameter. In my previous notation, it was 2 minus delta over, so 2 plus delta over 2 minus delta. Huh? Okay. Here, well, it depends on how you want to express it in terms, for instance, of V, so I didn't write the expression. Eta is positive, that's the point. Good. Okay, so I'm a bit embarrassed to do a correct review of the literature. Actually, getting exponential rate in kinetic equation is an old story. We have people in the audience who have participated to this long ago. For strongly confining potential, I already mentioned one of the papers of Ferro. Actually, there are two which are related, and the one of Moore and Neumann. But of course, if you look at the kinetic Fokker-Planck equation, the Vlasov-Fokker-Planck equation, it is a very old story. I found a paper of 1934 by Kolmogorov where he computes the green kernel, and it has been, of course, a source of inspiration for the whole hypoelliptic theory. For instance, there is this paper of Ilyin and Ashminsky of 1964, which is before the Hermander theory, where there are already quite a few things. There is the Hermander theory, which has been implemented and extended to cases which are more interesting for kinetic equation in this paper. So it's a long story. And it has also been used by people who were interested in application of these hypoelliptic ideas, not necessarily hypocoercive. And for instance, for Vlasov, Poisson, Fokker-Planck, there are nice mention of it in these old papers. So there are related topics. So I didn't mention the H1 hypocoercivity, which in my case is actually quite connected with the Hermander theory. There is the algebraic structure that is exported in nice ways. I mentioned Thierry Gallet, who coined apparently the word. And diffusion limits, of course, there is a whole literature, so that I cannot mention, but there are some people in the other audience there. Okay, and on the probabilistic side, there are plenty of things, but I'm definitely not the right person to list these papers. Okay, so let me go to the non-compact case. So what do I mean by non-compact case? Is the case where I miss one of the two basic assumptions, H1 and H2, which are the Poincare inequalities. So typically, when the external potential is 0, but there are other cases. Okay, so the question is, by what do we replace the Poincare inequality? And I will mention first, well, this case, and this Nash inequality, which is going to play a role. Okay, but there are other cases, for instance, with very weak confinement, where it's more Caffari Nirenberg type inequalities and moment estimates, or sub-exponential equilibria, where it's quite standard, at least in the macroscopic level, to use weak Poincare, but you can also use weighted Poincare or hardy Poincare type inequality combined with moments. If time permits, I will just show a slide on this. Okay, so first example, assume that you have no external potential. Okay, so you have, say, a nice Maxwellian in velocity, but nothing to confine the system. So the system spread. Okay, there is no stationary state, but eventually you are interested in the rate of decay of the kinetic equation. Of course, you have in mind the diffusion limit. So you know that it's the heat equation that is going to give you some information. So you expect T to the minus D over 2. Okay? One way of obtaining T to the minus D over 2 is, of course, Nash inequality. And actually, you can also implement it at the kinetic level. So here, the idea is, well, to do the abstract computation in the same way as before, keeping the ATP-FF instead of trying to control PF by a Poincare inequality. So I recall you that AF is computed by inverting T's equation, which tells you that in the Maxwellian case, for instance, G is given as a Maxwellian against a spatial density that I call UF, where UF solves the elliptic equation, which is here. And T's minus gradient X applied to the flux associated with the distribution F is just the TPF computed here. Okay, so I'm solving 1 plus TP star TP UF M equal TP star F here. Okay, so once you have this, you can use the equation which is here, there is no external potential, to get estimates that you can express in terms of this ATPF. You can also control the spatial density, but in terms of the L2 norm. And, well, the answer to what you can control by the right-hand side here, by the entropy production term, is given by the Nash inequality. So you can combine the term which comes from ATPF, which is here, with the L1 norm, which is actually conserved. It was in the previous slide, sorry, I didn't mention it. Okay, and you get that pi, the macroscopic part of, so the spatial density of F is controlled by the inverse of ATPF, where the inverse is just this quantity built on top of the Nash inequality. So what you are going to prove is that the two terms, the distance to the local equilibria plus this ATPFF, this good term, actually control phi of the entropy itself up to some constant here. Okay, so now you are in business, you can use a Grunwald inequality, reinject this, and that's the way you get a decay rate, which is now algebraic, and you get the T to the minus D over 2 rate. Okay, so this is done at the level of the Nash inequality, and this is the statement which is here. Okay, so I just anticipated on this. So you get T's decay for H, and using the equivalence of the norm, you get T's decay rate for the L2 norm, with weights which are to be well chosen, and here again you can use the spectral extension. So that's the kind of thing you get in terms of the original norms, and you have to be a bit careful with the spaces and the weights that you put. Okay, well, you can go beyond this if you use Fourier modes. So that was one of the motivation of this Fourier mode decomposition. Xi is now a vector in RD. You can use it, and if you have well-prepared initial data, for instance, which have zero moments, so you make the diff, well, you assume that the distribution function changes sign, of course, and has zero average. Then you get some improvement. Sorry, I went one too far. And for instance, you can get an improved decay rate by a factor 1, which is what you expect. So here, from the spectral point of view, it's far from being obvious, because I wouldn't know how to make a spectral decomposition in which you use moments with respect to the Dolbeault measure in X with these complicated weights on in velocities. I mean, this is not so straightforward. Probably there is a way of doing it, but I don't know how to do that thing. So it's nice to work in this reduced space in Fourier variable, make the estimates, get the decay, and then use spectral extension and get some rather nice and general results. Okay, so, oops, sorry, I have a problem with this. So as I told you, the game is to replace Poincare inequality by other type of inequalities. And we have two Poincare inequalities. The one in the, for the microscopic coercivity, which tells you how far you are from the local equilibria. It is the H1, the one which is related with the collision operator here. And typically, you can replace Poincare by weak Poincare, which is rather standard, or hardy Poincare, which is a bit less standard. And concerning the macroscopic coercivity, well, I already shown to you when that V is equal to 0, you can replace it by a Nash inequality. When you have external potential which are not confining, you can use weight and get weighted Nash inequalities or Caffali Cohn-Nirenberg inequalities with some typical moment weights. Okay, and well, the picture is now quite large because you can do it at the diffusive level or on the collision operator, or you can do it for the confinement, and there are plenty of cases. Okay, this is one slide. So what I have just shown to you was the case V equals 0. At the level of the diffusion equation is just the heat equation, so it's just the Nash inequality. And at the, sorry. Here it's just at the level of the diffusion equation when you have this. So V equals 0, heat equation, you have Nash inequality, you have the decay T to the minus D over 2. Now there are other cases. So the good cases, the compact cases, is when you have the Poincare inequality. So typically when you take a potential which is V of x equal modulus of x to some power alpha, alpha bigger or equal than 1. So you have a Poincare inequality now in the x position for the macroscopic variable. Okay, and that's the way you get this exponential decay rate. Now there are plenty of intermediate cases, so I just put some of them, not all of them. For instance, here there is a logarithmic growth with gamma not strong enough so that e to the minus v is in L1. Of course, there is also a case where e to the minus v is going to be in L1. Maybe you put 1 plus x squared here, and 2, gamma over 2, okay, anyway. This would, for instance, give some fractional diffusion limits, which are very interesting, but this is out of the scope of this lecture. There is also the case of this weak Poincare or weighted Poincare inequality, which typically corresponds to the case where you don't have the Poincare inequality. You have a growth of the potential which is not enough, but still you have weaker forms. And actually, I would like to mention this case. So weak Poincare inequality will give you a decay rate which can be taken arbitrarily large. Or if you use weighted Poincare with moments of order k, and I will show you in a second, then you get a decay which is explicitly of this type, which is quite nice because you see, if you fix k and let alpha get closer and closer to 1, so approximate the Poincare case, well, you get a rate which is faster and faster, an algebraic rate which is faster and faster, which connects well with the exponential rate that you have above alpha equal 1. So it is the picture at the level of the diffusion equation. Now, for the kinetic equation, well, the picture is more complicated. So I mentioned a few papers, not all of them. You have some lexicon here to use. We are trying to characterize some of the interesting cases, not all of them. So the compact case, again, is here. It's when you have the microscopic Poincare inequality, so you have a rate of growth of the potential. Well, potential is not the appropriate form. It's e to the minus v to some power beta, beta larger or equal than 1. Okay? So that's the microscopic Poincare inequality, and here the macroscopic Poincare inequality, that means that v has some growth which is large enough, or you are in a compact set, for instance, the torus. So for instance, for the torus, you can refer to the paper of Michler and Moore. Okay, so there is this case here, which is sometimes called sub-exponential, but you have to be careful. It's sub-exponential in x or sub-exponential in velocities. So you have the two cases. And you have the weakly very weak confinement case, which is here, and so on. Okay, so plenty of things. It refers to inequalities which have been studied for a long time, at least from the diffusive point of view. I just mentioned a few entries in the literature, but not a whole review. Okay, maybe one, yeah, I have to be careful with this. Okay, so one cases of very weak confinement. So it's almost Nash, but not exactly Nash. So let me show you what happens. So here you have a potential V, which has some logarithmic growth, but the growth is not so big, so gamma is going to be taken less than D. E to the minus V, at least away from the origin, is not integrable. If you want to take into account the origin, you can replace modulus of x by this, of course. And essentially, what matters is the growth at infinity. Okay, so that's what we call very weak confinement. It's not really confinement because it's not enough to produce a stationary state, which is in L1, okay? But still, there is the diffusion doesn't take place as fast. You expect it doesn't take place as fast as for the heat equation. Actually, this is more complicated. It depends on the assumption you make on the initial datum and on the space on which you work. So let me, okay, so I just mentioned that we are here now, and we are going to use Kerr-Farley-Kohn-Nirenberg inequalities with some moment estimates and get this decay rate, which is what is expected generically, but in some cases you can do better. Okay, so here is an example where you do better. Oops, what is going on? So I'm lost. Yeah, here it is. No? Yes. No? Yes. No? Okay, here it is. Okay, so you recover, well, the rate of the heat equation here. If you work with these norms, provided gamma is not too big and it's strictly less than D here, as you can see, at least in dimension bigger or equal than 3. 1 and 2, you have to be a bit more careful. Okay, so that's another story. Okay, so the idea is that actually the rate is given by the Nash inequality, but the constant is modified. Okay, another result is when you assume that you have moments here of order k, and now you can take gamma arbitrarily close to D. Okay, and in that case, you get what you expect, D minus gamma over 2. Still another case. Well, if I manage to do it. No. No. What? Come on. Sorry. Yeah. No, I skipped it. Sorry. Okay. If if you have some homogeneity, and that's there, it's important to take gamma log of modulus of x. Then you can do some rescaling. Okay, and then you have a nice problem in rescaled variable, in self-similar variables. So you can use Gaussian weights. Well, in that case, you get still another type of result where it's very natural to assume that your initial datum is bounded by some Gaussian or stationary solution here. Okay, and in that case, you can do plenty of interpolation between the L1 norm and the L infinity norm, and you get rates which are even better, at least in some cases. Okay, just very quickly, a proof in the case, why does Nash appear when gamma is very small? Well, just because you can make a change of weight here. So you put the weight inside the function. By doing this, you get a Laplacian V, so you have to compare these quantities, or you just compute directly this quantity, actually. You get this Laplacian of V, and this is like a RD term. This RD term is controlled by the RD inequality by this term. So actually, you can just omit this term, so Nash wins. Okay, Nash gives you the rate, not the constant. Okay, now, moments, still at the level of the diffusion. Well, you can compute moments and get some growth of the moments, and you can combine them with weighted L2 norms, so with also moments here, using not anymore Nash, but Kerr-Farley-Kohn-Nirenberg. This is a quite natural idea. Huh? So if you do this, that's the way you get the rate t to the minus d minus gamma over 2. Huh? And you have, of course, to take into account the coefficients. Okay, sorry. So time is running out, so I should probably go to my conclusion. I will skip anything concerning sub-exponential equilibria, but I want to show you two slides about Vlasov-Poisson-Fokker-Planck equation. It's a setting in which the L2 hypocoercivity method applies, and I think this is quite interesting. So let me mention that some results about Vlasov-Poisson-Fokker-Planck in the nonlinear regime have been achieved by Hero and Thoman and Herda and Rodriguez with smallness condition, essentially. So here it's a joint work with these people. And okay, so what is Vlasov-Poisson-Fokker-Planck? Well, it's just the Vlasov-Fokker-Planck inequality that you have seen before with the Fokker. I take the linear Fokker-Planck with Gaussian local equilibria, except that you have an external potential that you modify by the self-consistent potential of the particles. So here I'm assuming that V is a good potential. It's a confinement potential, so it prevents the runaway of the particles at infinity. But it's modified by the self-consistent potential, which is the nonlinear term in the equation. So the first thing you can do is to linearize. Okay, so this is what is done here. So essentially you expand around the unique equilibrium. So you have to assume that V is confining enough so that you have a well-behaved local equilibrium. And you write an equation for H. So H is actually the quotient of F minus F star minus 1 up to the factor eta. And if you replace it here, you get this term with a left-hand side which doesn't depend on the parameter eta, and with an eta here for the quadratic term. So the first thing to do is to linearize. So just drop this eta term, and you get the linearized Vlasov-Poisson-Fokker-Planck equation, which is here. Okay, so the difference with the previous term is that now, well, I have to take into account a term which comes from the Poisson equation. If you linearize properly, that's what you get, which is not what was done in the papers I mentioned, and that's why they had the small mass condition. Next slide, if I can. Okay, so this fits with the diffusion limit. I have no time to explain this. And, well, you can do, oh, sorry, I was a bit too fast, sorry. Let me go back, if I can. Okay, an important thing here is here. So you use the natural L2 norm, which is based on the stationary solution, the one in which you solve the Poisson-Boltzmann equation. So it's really the stationary solution of the nonlinear problem. And H, remember, is essentially F divided by F star minus 1. Okay, so it is this usual weighted norm with the weights based on the stationary solution. But you have also a perturbation term that comes from the non-local term due to the Poisson equation. So that's the new thing here. This is the basic norm. Now, to apply the hypocoercivity method, you have to redo everything. Okay? So you have to perturb, you have to introduce the twist with this operator A, okay? And everything works well, except that you have to reprove all the estimates, including the non-local term that comes from the Poisson potential associated with the stationary solution, or including the Poisson term, which comes from the perturbation. Okay? It turns out that this L2 framework is really robust with this, and this works. So this gives a standard hypocoercivity result with a constant C which is bigger than 1, and a rate which can be explicitly computed, but which is probably not so, well, it's not so bad. Because when you look at the relation between the entropy and entropy production, this is a coercivity result. And the best constant gives you the best rate you can expect. And now you have the correct linearized operator, so it's a good candidate for the rate for the nonlinear problem. Now, for the nonlinear problem, there are issues. You need a regularity estimate to be able to prove that you can really Taylor expand and use the linearized problem. This is something which is not done in dimension 2 and 3, but can be done in dimension 1. Sorry, so just skip this. This just tells you that the method is consistent with the diffusion limit. So what you get in terms of estimate for the rate doesn't see the scaling parameter when you make the parabolic scaling. Okay? Estimates are uniform in the epsilon. Now, the important thing is here, so if you are in dimension 1, then you have plenty of estimates which are enough to control the convergence. And then using the modified norm, the h function, you can prove that you have the exponential decay also in the nonlinear case. So, okay, this is a small result. Okay, so usually when the dimension increases, the Poisson equation becomes more and more complicated because of the kernel of the Laplacian, the green function of the Laplacian. Now, when you do this estimate, it's exactly the opposite. Dimension 3 is easy in terms of estimate. Dimension 2, you have to be quite careful because of the logarithmic kernel. And dimension 1 is really a mess because of this linear growth of the kernel. But you can do it, but you have to be very careful. In terms of regularity, of course, this is the standard picture. So in dimension 1, it's easy. In dimension 2, it is probably a special case. I have not been able to find in the literature enough estimates which are valid for large times to control, but I think it is really doable. Dimension 3, so far, with what I know, it's out of reach. There is a new idea which is needed. Okay, so sorry for being a bit long. Let me just stop here. You can find the slides, they are already online, and I will be happy to answer your questions. Thank you for your attention.